Wonderful to be here. Yeah, I've got the sound, got the mic. So I'm Martin Herbordt. I'm a professor at UCE at Boston University. And I'm going to talk about FPGAs. I guess that's a surprise. It's amazing. I think this is the third. Can you hear me? Sorry.
Yeah, a little closer. Thank you.
Yeah, this is the third FPGA talk of this session, and there were multiple talks yesterday. This is amazing, so exciting, and some distinguished members of the community as well who are here as part of the advisory board. So I have been, I'm not sure why, maybe it's because I'm the most senior, but I have been elected or selected to be the presenter for a group of faculty at Boston University who are interested in reconfigurable and real-time systems. Those are Manos Athanasoulis, Alan Liu, Renato Mancuso, and Rich West. This talk has three parts. One is to give a sense of what we do as a group. Another is to give some background into the types of problems that we look at. And the final piece is to do an IUCRC specific task, which is to present a specific work that can be done by, say, a student or two in a year. And for that, Sahan Vanderout will be presenting, since he's the one who came up with the project and is doing a lot of work. And I'll probably refer to see him yesterday as well. So here's who we are. Manos is in computer science, along with Renato and Rich. Alan and I are in ECE. You see that we all have interests in computer systems. We're all interested in reconfigurable computing, and I have used sort of the very sophisticated graphics of having the color be the same for areas where we have a lot of overlap, and perhaps even a collaboratory project. Speaking about collaboratory projects, so I've done another very sophisticated graphic showing some of the projects that we have in common. So those include real-time systems, where Renato and Rich are world leaders, intelligent memory controllers, where Renato and Manos have a wonderful project. Alan and I are both interested in switch application processing. And why don't I go to the top, which is sort of what is pulling us all together. And that is that we're all interested in processing data while it's in movement. And whether it's in the NIC, in the switch, or in the memory controller, or probably anywhere else. We have, so one of the specs was to talk about industry collaborators. So these are many of our industry, I think probably not exclusive, but many of our industry collaborators. And maybe I'll call out Red Hat especially for supporting sort of a large fraction of what I'm going to talk about today. So the next part of the talk is to introduce, the IUCRC specific project, offloading hypervisor functionality to an FPGA-enhanced SmartNIC. So Sahan will do the bulk of the presentation about this, but first he asked me that perhaps I should do the motivation and some of the background, so I'll continue for another minute or two. So we know that, as you've heard for many talks already, and you all know because this is your area, data centers are evolving. They're going from, as some literature says, from being compute-centric to data-centric, or we might say network-centric, or I would even say data movement-centric. And that has given us a revolution in data center architecture, and I would say that this revolution is manifest in intelligence everywhere where there is data movement. And so I've just circled a bunch of the places. Miriam gave a nice talk about network-facing NICs. We also have been doing, well, she also talked about FPGAs and switch as well, which is also something again that we and Alan Liu are very interested in. These data center enhancements have lots of extremely stringent requirements. You're running at, well, what are network packets running at? Hundreds of gigahertz. And you're processing at that speed, and you're doing complex processing, and flexible processing, and processing multiple streams, and you're trying to combine data. Clearly, you need hardware speed with software flexibility. And this is, of course, where FPGAs come in. Well, that's the data center, but you just take a look at IoT and the edge, you have the exact same requirements. So where we are is that we have new processing paradigms which have motivated new hardware capabilities in data center, the edge, and in IoT. These hardware capabilities are based on smart data transfer fabrics, including, well, as I say, NICs, switches, memory controllers, and they're enhanced invariably with FPGAs. So the key point, and so this is motivation, but where we're going with this is that we have all these wonderful new capabilities, we have all these toys, we have all this great stuff going on in the data center and on the edge, and we have a bunch of applications that have driven the hardware. So now, how do we reverse it? So how do we use all these capabilities to do things that, well, that are new and that we perhaps haven't been thought of before? And, well, but first, as you all know, those people who are not FPGA people, and especially those who are, well, we know that there are various issues, if we can put it that way, in data center, in FPGA development, infrastructure, and so on. So wouldn't it be much easier? So what are some of the problems? So some of the problems are that, well, it takes a lot of expertise. We would like to have faster turnaround, not many hours. We'd like to have consistent APIs, which would give us better application portability and enable more complex usage models, and so on. So the problem, or one of the problems that we address in sort of our broader research is, well, it's caused by the current state of the hardware operating system. So some people call it the shell or the donut, or just the infrastructure that takes the FPGA to be usable. We see here that we have a couple of different uses, one from Azure, one from AWS, one from an IoT environment. Well, that's great. They're all wonderful, they work, they're specific. That's also the problem. That means that these systems are sitting sort of where operating systems were in the 1960s, where every company had an operating system for its own computer. And so our project, so our global project, our big picture project is the following. DISL, Dynamic Infrastructure Services Layer, otherwise known as a hardware operating system generator. At this point, I will turn it over to Sahan. I should say that we also have a poster. So the poster's yet something different. The poster is exactly on this. And another student working on this project said Tahir will be presenting that. So I invite you to visit that poster during the 5 o'clock session.
Thank you very much. My name is Sahan Bandar, I'm a PhD student at Boston University. So that Professor Herbordt has established that the current existing solutions are not that good. So what are we proposing? So the Dynamic Infrastructure Services Layer is an automatic framework to generate hardware operating systems and BIOS components. So it will take a component library and user constraints, the user requirements like the deployment configuration, constraints, and target applications, and generate an operating system and BIOS component. So why are we differentiating between these two things? Is we would like the operating system component to be fully device independent, and the BIOS component to include all the files and other device-specific details, so that we can port the same operating system across different devices, just like software operating systems. So in practice, this will pick different components from a library of components and connect them all together with a highly flexible interconnect to generate the system. So what can we build on top of this hardware operating system? What interesting applications can we do? So let's start off with one of the more ambitious ones. So let's talk about hypervisors for a bit. So they're big and complex pieces of software which expands the trusted computing base and increases their attack surface. So a compromised hypervisor can corrupt or leak guest data from guest memory. What if we don't allow the hypervisor to actually manage the guest memory? So offloading some parts, some functionality of hypervisors have been explored for a while. So there's prior work on offloading network services of the hypervisor, and offloading management of bare metal guests to the NIC. And currently, some of the cloud service providers offload most of the virtualization and security functions to DPUs. So, can we offload some functionalities to FPGAs, SmartNIC FPGA in this case? So let's start off with memory management. So in the model we are proposing, an application running on the FPGA handles setting up all the memory structures in the host memory. The host is only responsible for compute tasks. The FPGA is network attached, so it can be managed remotely. The host will not have any ability to manipulate the FPGA memory or change its configuration. The host can use standard interfaces like Vertigo to make requests from the FPGA for different services. And network and storage functions could be other potential candidates to go through like this, and even more management functions on the line. So what does this will provide in this scenario? It provides faster direction to execution environment, which is physically separate from the host machine. And it manages all communication with the host, and it provides services such as memory network to the offloaded functions. It should also provide other primitives to establish trust between the FPGA and the host, such as testing that the experience will be hardware OS and the application kernels are not tampered with, etc. Because the host should trust the FPGA before it allows it to manipulate its memory. So let's talk about two other more simpler examples. Secure application. It's simple. Apart from all the good things I talked about in the previous application, the hardware operating system can schedule different applications inside the kernel using modular information. And then network firewalls for a SmartNIC FPGA. You can accelerate the firewall functionality using custom accelerators and change the rule sets dynamically because of the configurability of the FPGA. But the real power of the hardware operating system comes where we can schedule all of these different applications on the same FPGA and even port these applications across different devices without really changing the application. Because the OS layer is providing the support services for these applications so that the application developer can just focus on either writing the acceleration engine for encryption or the hypervisor overload or the network firewall, and not worry about building a full stack of hardware every time you need to build these applications. Thank you.
Any questions?
Everybody see filling out their make it. Yeah, there's some people online, so it might be going through.
So now your goal is to offer resources and services in your shell, the hardware operating system, right? And so how does that affect portability? Would you, for each different device, you would have to port all your operating system stuff around that? Then you still have to compile your design into the FPGA, right?
So that's why we have made it very sort of an important that we differentiate between those two layers. That's why we wanted to highlight that there's the OS component and the BIOS component, which is like something similar to a software operating system. There's the architecture specific code and the non-specific code, the kernel. So just like that, we would like the operating system to be fully independent of the underlying device, but only the device-specific stuff, which is in the BIOS, should be changed when you're porting to a different device. So everything above that should. So this is the vision, right? It's not done yet, but it should be portable across different devices, and then the applications running on top of the OS should also be portable because it's just using those interfaces provided by the operating system and not the lower-level interfaces.
Right. Okay. So then the BIOS, you're saying the BIOS part is the layer that talks to the outside world, and then the OS part is parts that talk to the inside of the FPGA. Do I have that right? Or?
Well, the BIOS part would include everything device specific. So your files, and then any other logic surrounding the file to implement any necessary functionality and provide consistent interfaces to the OS component. And the OS component will just use those consistent APIs, like interfaces provided by BIOS component. And then it would again provide a set of interfaces to the applications which are running on top of that.
Okay.
Yeah, there's a lot of meta in it. Because the dream is always to have a universal hardware operating system. You can't.
Sure.
Because every hardware is different. And so the nature of the project is, and Ahmed, who spoke yesterday, is this big.
I was trying to differentiate your what you're calling things.
So
Like a BIOS.
we settled on operating system generator as being reasonably descriptive of what we're trying to do. So since every hardware is different, it's going to have different IPs because Xilinx isn't going to give us everything.
Yeah, I hate that.
And
We should give you everything.
they really should. But since they're not going to give you everything, you're just going to have a hard IP layer that you're going to have to build.
We should make our own FPGA.
I think that would be a great IUCOC
I had
project.
something
Hi, I'm sorry, I missed the whole meta thing. The generator is generating hardware that implements those functionalities.
Yes.
Cool, that's really cool.
So the low-level BIOS part is something written by hand, and then the OS part is generated, or,
No, both will be generated because so we can have component libraries for all those files and IPs, all the other ones as well.
memories and.
Yeah, so those could be also connected automatically using a generator.
There's also an amazing piece that Ahmed and San talked about yesterday, which was Third.io. So actually, you talk about the Steer project, but the idea is to use the universal driver. In other words, to do what Red Hat would do or an open service provider would do. And that is to use the universal driver so you don't have to write all your own. And the solution involved, and one of the nice things is that if there's anything that you can make into a virtual device, it's an FPGA, because an FPGA is configurable, you can make it into anything you want. And so you can make, so from the host operating system point of view, the FPGA is a virtual device. That's if I understand that correctly.
Yeah. So because the birth, so we are using Vertio because they do differentiate between embedded devices and physical devices. You can just portray as a virtual device with the operating like driver, and this actually be a physical device.
What is the primary benefit that you're going for with this work? Is it the separation of the host operating system from the guests?
So I think the primary benefit is improving the usability. So the features are different, difficult to program. So if you have this, and the difficulty comes mostly not from developing the application logic itself, but having to develop the whole stack every time you have a new design. You have to implement all of these low-level controls. But we don't have that problem in software OS, because the OS provides all these services. So have a similar model for FPGAs, I think that would be a good product.
But also, you said, also the other point that you said, it's also the interface to the host. So you're able to use the universal driver to talk to the FPGA.
Okay, but you're talking about the FPGA, but if I have a server, I want to host numerous guests, why would I use this versus the general purpose computer? That's the part I'm trying to understand. Is it just you're trying to make the use of an FPGA in this environment easier?
Yes. Yeah. So this is specifically for FPGAs.
Got it.
Yeah, I just, I think, hopefully I don't make things more confusing, but the big piece is the developer of the FPGA to make it portable across FPGA devices. But as a side effect, but the work that Sahan has done also gives you more ease of use from the point of view of the operating system provider.